Hello and welcome to your Chem 212 Organic Chemistry video lecture notes. My name is Kelly Bobinger and I am going to be helping you through this organic chemistry experience and adventure. One of the things I want to let you know right off the bat is to help you understand the material we're going to go through in these lecture videos is it would be best for you to actually read the textbook first. That way, when you go through the slides, you're not going to be surprised at what comes at you. You'll already have a little bit of information in knowing what's going on. The goal of these lecture notes isn't to present the material the first time. The goal of these lecture notes in this video is to help clarify some of the information you've already learned and help you out with it that way. So if you haven't already, I suggest you pause the video and go ahead and read the first chapter of your textbook and then come on back and we'll see you soon. All right, if you have already read the textbook, chapter 1, we'll go ahead and get started. Another point I do want to make is my lecture notes are written based on the McMurray Organic Chemistry textbook. We're going to start off talking about structure and bonding. Organic chemistry, until the mid-1800s, referred to basically organic compounds made from living sources, and they called other mineral sources inorganic chemistry. Wollier in 1828 showed that urea, an organic compound, could be made from minerals. In fact, he was able to synthetically make urea, something that is a natural compound, and that's where we were able to start up with our organic chemistry model. Today, organic compounds are those based on carbon structures, and organic chemistry studies their structures and reactions. These include biological molecules such as drugs, solvents, and dyes. It doesn't include metal salts and minerals. That would be the inorganic class. And this last part here about polymers, organic chemistry does not include materials of large repeating units without sequences, but we will have some polymers with sequences, and we'll be taking a look at those later on. So the first couple chapters in your textbook go over material that we've learned back in general chemistry. So the first couple chapters are basically a review of the material. If I go over any material that you need to go back and refresh your memory on, go back to your inorganic, your general chemistry textbook. In fact, most organic instructors skip the first 2 chapters and go straight to chapter 3 because that's where the OCHEM really starts. Or with online, you can probably Google some of the information and get a lot of that too. All right, let's take a look at Lewis structures and review those. For organic chemistry, the octet is the most common structure we're going to have. We're not going to have any expanded octets or anything like that that you've seen in general chemistry. So keep in mind, octet is the most stable, and that's what we're going to look for. So let's go ahead and look at some nonmetals, and we're going to talk about how many bonds they can make and also what types of bonds they can make. Well, organic chemistry, let's start off with carbon. We have 4 bonds. Carbon makes 4 bonds. It prefers 4 bonds. It can make single, double, or triple bonds with other carbons. Now remember, it has to be a total of 4 bonds. So if carbon only has single bond, it would have to have 4 single bonds. If it has 1 double bond, it would have to have 2 single bonds to be a total of 4. It could have 2 double bonds, that would be 4 total. If it had a triple bond, it would also have to have a single bond with it to be a total of 4. So that's how we're going to look at this chart here. Nitrogen prefers 3 bonds. I know with nitrogen we can also have a quaternary situation where it has a plus charge, a formal charge of +1. We'll get to that more later. So at this point right now, let's keep in mind that nitrogen, once it's octet, most stable, 3 bonds, that type of thing. So because nitrogen can have 3 bonds, it can have 3 single bonds, it can have a double with a single, or it could have a triple. Oxygen and sulfur, these are 2 other elements we'll run into with organic compounds. They are in the same group on the periodic table. Notice sulfur is just below oxygen, and they both prefer 2 bonds. Again, I know sulfur can have expanded octet. We are not going to be talking about that right now, maybe later on in this semester, maybe even next semester. So right now, let's take a look at these 2 having 2 bonds, the preferred number of bonds. So that means either oxygen or sulfur can have 2 single bonds or 1 double bond. Hydrogen always, always, always one bond, always, always single bond. If you're ever putting together a Lewis structure and it looks like hydrogen's going to have two bonds, it's wrong. It's never going to have anything other than a single bond. Same goes for those halogens. We do have halogens in a lot of our organic compounds, and they also only have one bond, a single bond. So if, again, you're never going to put, when you're trying to get an idea on Lewis structures, on putting together your structure, you're never going to have halogen with two or more bonds, always single bond. So what we're going to do now is draw the Lewis structure for the following, and I have 3 examples here. So throughout these video lectures, there's going to be times where I'm going to have you go ahead and pause the video and try something on your own, and then you're going to come back and check your work. So that's going to be similar to what we're going to do here. I'm going to go ahead on the next slide, show you my version of how I do Lewis structures for one of them, and then after I do that, I'm going to have you pause the video, do the Lewis structures for the other 2, and you can check your work. Now, if what I do as my examples isn't enough for you to recall how to do Lewis structures, then again, I suggest you go back to your textbook or go ahead and look this up online so you can get really good at these. Okay, go ahead and pull out a separate piece of paper. I'm going to go ahead and show you my technique for drawing Lewis structures. Right off the bat, I'm going to apologize. These are going to be very crude drawings because I'm using a pad here, so sorry about that. That's just the way it's going to happen. So the first thing that I do is I write down the structure, or the molecular formula of what I'm going to do the Lewis structure for, and then I make a table. And this table, what's going to happen is I'm going to, in this box here, write down each element and how many I have. So carbon, I have 1 carbon, and I'm going to multiply that out by the number of valence electrons it has. It has 4 valence electrons. And you can tell that if you count across the S and P block on the periodic table. Don't count that D block, that part that dips down, those transitions. If you count across the 2 columns of the S and then you get to the P block, if you just count across there, the top number up there tells you how many valence electrons there are. So look at a periodic table and look on the top and you'll probably see the number 4 on top of the column that has the carbon on there. So the first thing I need to do is make a table where I can establish the total number of valence electrons, because it's important for me to show all the valence electrons. In fact, it's the valence electrons that are involved in bonding. And I have 3 hydrogens in my formula, 1 electron, that's valence electrons for hydrogen, so that gives me 3. And the last one, bromine, the halogen, it's in the 7th column over. So I have 1 in my formula, so it would have 7 valence electrons. And if you notice, if I take this and I total it up, I have a total of 14 electrons I must show in my Lewis structure. So that shows me how many I'm supposed to show. Well, another thing I like to do, and this was from the slide before, is I like to keep in mind how many bonds everything must have. So over here, I'm going to write number of bonds. And carbon wants 4, hydrogen 1, and the halogen 1. So the reason why I do that is when you have more than 1 carbon or you have something that needs more than 1 bond, one of the best ways, one of the best strategies to start putting your Lewis structure together is to go ahead and put things that need most number of bonds together. You also want to keep the things that only have 1 bond, such as hydrogens and halogens. You want to save those till last and kind of put them around the outside, or they're going to be terminal atoms anyway because they can't be bonded to more than 2. Now this is a pretty simple structure. We only have 1 carbon and we have a total of 4 things that have a single bond. So you pretty much know the structure already. Remember, the idea here is I'm showing you a technique, and I purposely used a compound that you most likely know the structure, so we're learning technique. All right, so the next thing I do is I write down whatever needs the most number of bonds. Carbon. Keeping in mind with Lewis structures, we can write them with a bond on the top, bottom, left, and right. I have 3 hydrogens and 1 bromine. Because we learned back in general chemistry that this is a 3-dimensional structure, it really doesn't matter if I put the odd man out, bromine in this case, on top, bottom, left, or right. It's all equivalent to each other. So I'm going to go ahead and just put bromine on the right side here. Around here, remember on Lewis structure, we've got top, bottom, left, and right. So the next thing I do is I propose a structure. I don't really bond it yet, keeping in mind how many bonds each thing must have. So carbon looks like it'll get its 4 bonds. Hydrogen, single bond. and bromine single bond. So the next step is to join by single bonds. And if you noticed, I used 8 electrons. So total, I've used 8. That means I have 6 more that I still have to show. Where do those 6 go? Well, remember, hydrogen is a duet. It can never, ever have more than 2 electrons. That poor hydrogen only has 1 little proton in there, and it's holding on to 2 electrons already. So that's already doing a lot of work. But this bromine right here, he has a lot more protons in there. He can handle them. In fact, if you keep in mind, all of the halogens will have a single bond, and the halogens will have 3 lone pairs around them. So when we're doing the Lewis structure, I just showed 6, let's go ahead and take that off. We're doing the Lewis dot structure, this is what it would show. Now sometimes, in fact, it's a lot easier to go ahead and once we know that we have a single bond between the hydrogens and the bromine, we can just show the single bond with a line like this, and each line represents 2 electrons. And then if we still need to show the lone pairs around the bromine, we can go ahead and do that. So sometimes you need to show the lone pairs and sometimes you don't. Now this is expanded. We're showing you explicitly all the bonds, and also as we go along in organic chemistry, we're not going to have to do that much detail. All right, so we're going to go ahead and do the next one, C2H6. I would recommend you pause the video, use this technique. When you come back, I'm actually going to have the whole slide ready to go. So all I have to do is talk you through it, and you don't have to wait so much for me to write. And also, again, I pre-apologize for my handwriting. So go ahead, pause the video, try to do the Lewis structure of C2H6 using this technique. All right, I'm going to go ahead and show you my table for this. We have 2 carbons, 4 valence electrons, that's 8 total. Hydrogen, I have 6 in my formula, 1 valence electron apiece, 6 total. So adding those together, I get 14 total. It just so happens I'm using small molecules. You normally don't always get the same number 14. That just happens to be a coincidence. All right, carbon needs 4 bonds, hydrogen needs 1. Now here's the thing, I have 2 carbons in this formula. I have to show both, and I must show all valence electrons. When you have 2 carbons or 2 things that need more than 1 bond, you usually start off by putting them together. So I'm going to go ahead and imagine I'm going to have these 2 carbons bonded with each other. So that would give this carbon 1 bond right now and this carbon 1 bond, only 3 bonds left for each of them. We'll take a look at this. How many hydrogens do I have? 6. So what's going to happen is, again, I'm going to imagine what my structure is going to look like. This is a trial and error. It could be you try something and you realize that the bonds aren't going to work out, so you try again. So I have 2 carbons, yes. 6 hydrogens, yes. Let's see how many electrons this works. So let's join by single bonds. That would be 2 electrons for each of these. Sorry if you really can't see them. If you take a look, I used 2, 4, 6, 8, 10, 12, 14. Used them all. I'm all done. That is the Lewis dot structure for C2H6. If you want to go ahead and show this with the bonds not being dots, but the bonds being single lines representing single bonds, you can go ahead and do that. Technically, what I have up here is called Lewis dot. This is called a Lewis structure. Depends on what you're asked to do. All right, I'm going to do CH2O next, and as I did before, I'm going to go ahead and have you pause the video, try this technique on your own. The next one does have a multiple bond, so I'll show you how to work through that one. But go ahead and see how far you get with this. All right, be back in a minute. All right, here's my table for CH2O. On the word total down there, I didn't want to have to erase and start over, so I wrote over it, and it's really sloppy. Sorry about that. Let's take a look how your table went. Carbon, there's 1 in my formula. 4 electrons, valence electrons, gives me 4 total. Hydrogen, there's 2 in my formula. Each has 1, that's a 2. And oxygen, he has 6 valence electrons. There's only 1 there for 6. The total is 12. So keeping in mind I must show all valence electrons, so I need to show 12 electrons. In terms of number of bonds, on these number of bonds, guys, you're never going to total these. This is just a reference to make sure your structure, carbon has 4, hydrogen has 1, and oxygen has 2 in this case. You'll never total these up. This is just something to reference against. So we see that oxygen has 2 bonds, carbon has 4. They both need more than 1 bond. So the idea is my technique is to go ahead and put these two together with each other. And anything that only needs one bond, you always wait till last. So I only have one carbon and one oxygen, so I'll go ahead and I'll have those next to each other. Now, as it stands, if they each only had a single bond between them, then oxygen would need one more bond and carbon would need three more. That's a total of four things single bonding, but I don't have four things, I only have two. So as soon as you have a situation where it seems like you don't have enough of either hydrogens or the halogens, then you suspect multiple bonds. And we did learn on the previous slide that carbon can double bond and oxygen can also double bond. So what we're looking at here is a double bond between carbon and oxygen. So I'm not going to draw that in just yet. I'm going to show you my technique on how to fill that in with the Lewis dots in just a second. But keep in mind, remember, we're going to keep in mind if oxygen can only have two bonds and it's going to double bond, then this oxygen can't have any more hydrogens. Now, if this carbon double bonds to this oxygen, it's lacking two bonds. That means these two hydrogens, yep, you guessed it, they're going to go to the carbon right here. So don't add extra elements that aren't there. You only have these to use, but you must show them all. All right. This is my proposed structure, and I'm in my head reminding myself this most likely will be a double bond, but let's see what happens with our 12 electrons. First step is to join by single bonds. I'm going to join my hydrogens. I'm going to join my carbon and oxygen. 2, 4, 6. I have 6 more than I have to show. So the next step is on this technique is after you join by single bonds is put remaining valence electrons around terminal atoms. Remember, hydrogen can't take it, but this oxygen sure can. And we did the same thing with the bromine on the first example, if you remember. I used 6 more, so I'm done. I've shown them all. Now, this is all the electrons I have. And I want you to notice that oxygen has his octet. Remember, octet is the most stable. This carbon does not have an octet. Take a look at that. He only has 6. And then we have another thing wrong with this. How many bonds does it say carbon must have? 4. Right now I see it having 1, 2, 3. So it's lacking a bond. And oxygen, even though he has his octet, does he have the right number of bonds? Nope, he's missing one. In fact, both of these are lacking a bond. And we also thought, hey, these are probably going to double bond with each other. So what you're going to do is move a lone pair. Now the lone pair that you move would be one around the oxygen here. It doesn't matter which one you move. So when you move it, now I don't know if this is going to work. I'm going to scratch these out and I'm going to move it right here. And if you notice now, this oxygen still maintains its octet. And when I move those, I now gave carbon its octet. Hydrogen always only has a duet. So I'm just going to be circling the atom, the actual element, with its octet or duet. And take a look at that. Everything matches. I have an octet around carbon and oxygen like I'm supposed to. Carbon has 1, 2, 3, 4 bonds, and yes, it can have a double bond. If it has one double bond, it has to have 2 singles. Oxygen can only have 2 bonds total, so it has a double bond. That works, but he has to have his octet, so he also has 2 lone pairs. Hydrogen has its duet in both cases. So that's a very good structure. So let's go ahead and rewrite this as showing the bonds with lines instead of dots. So I would have carbon double bonded to oxygen, and oxygen would have its 2 lone pairs. And then hydrogens would be bonded to this carbon here. And so this would be the Lewis structure for CH2O, and the one above it would be the Lewis dot structure without these circles where I was trying to emphasize the octets. Again, if you're having any difficulties or you want to practice this some more, definitely look in your Gen Chem textbook if you still have it, or you can probably look up Lewis structures online, Google it. I'm sure there's a lot of good places for you to practice that. Atomic structure. So we're going to look at what does the atom look like. Well, we know that the nucleus has protons, and those are positively charged, and neutrons. In fact, the protons and the neutrons are what contribute to the mass of the atom. Outside that nucleus, we have electrons, and they're negatively charged. And because they're so tiny relative to both the proton and the neutron, we basically say they don't weigh anything because it's just not significant enough. Atomic number, that would be equal to the number of protons. Oh, and here's a picture here showing you the nucleus of protons and neutrons and where those electrons are. The mass number is the protons plus neutrons. And we can have a situation, in fact, we have it with many of the atoms, we can have isotopes. Now, what identifies an atom is its number of protons. So if you happen to have an atom that weighs differently, remember the only two things that participate in weight are protons and neutrons. Now, the number of protons identify the element. So if I have two elements, such as chlorine, for example, that weigh differently, it has to have 17 protons or it's not chlorine. So the same thing would go with carbon. Carbon has to have 6 protons or it's not carbon. But we have carbon 14, we have carbon 12, we have different weights on there, and that comes from the number of neutrons. So those would be isotopes of each other. Carbon 12, carbon 14, those are isotopes. They have the same number of protons, but a different number of neutrons. So when we take a look at what's known as the atomic weight or molar mass, it is a weighted average of the isotopes. It's based on their percentages, and that's why most of the time on the periodic table we don't have a nice whole number for the atomic mass or the molar mass. We actually have some sort of a decimal number with it. All right, now that we know what is inside the nucleus and what's outside the nucleus, let's take a look at the atomic structure a little more. We're looking at different orbitals based on where the electrons are located. And this is, again, the same stuff you learned back in Gen Chem. So we have 4 different kind of orbitals. They're S, P, D, and F, and those are always written lowercase. The S and P orbitals are the most important in organic chemistry. In fact, if you find carbon, you'll see it's in the P block, and it only has 6 electrons. We never get to the D and F with carbon, and that's kind of a nice advantage to us OChemists. We really only look at the S and the P. The s orbitals, those are spherical, and there's a nucleus at the center of that. There's only one s orbital shape. Whereas in the p orbital, we actually have kind of a dumbbell shape is typically how it's written. There's a node in the middle, and the node is when they calculate, the probability of where the electron can be, they found that the node has 0 probability that the electron is there. So typically it's shown with a dumbbell or maybe 2 spheres, one on top of the other. So the p orbital, there's actually, remember, there's only one s orbital, because if you rotate the s orbital along the x, y, and z axis, if we had a graph, a 3-dimensional graph, you couldn't tell if we rotated, it'd look exactly the same. But let's take a closer look at the p orbital. The p orbital, there's actually 3. We have a p orbital along the x, y, and z axes. And what happens is these 3 orbitals come together, and that's why we have 3 2p orbitals. You can see that on the graphic representation here. Now, how many electrons total can be in each orbital? 2. So back on the s orbital, since we only had 1, 2 electrons maximum will ever be in an s orbital. We're going to talk about where those electrons live on the next slide. So on the p orbital, each of these, your px, py, and pz, each of those can hold 2 electrons, which gives us a total of 6 electrons that can be held by your p orbital. This should start looking familiar to you. This is the distribution of electrons in an atom. What happens, and we'll talk about the rules in just a little bit on this, is our lowest energy, that would be down here on this, it says energy increases as we go up here, is the first shell that gets filled is a 1s, and it can hold 2 electrons maximum. After that, we don't have any p orbitals in the first level. We only started in level 2. In the second shell, we can have 8 electrons total, and that would be a 2s orbital that can hold 2, and each of these p's can hold 2, so that's a total of 8. And when we get to the third shell, 18 maximum, and you can see we have an s orbital for 2, one orbital that can hold 2 electrons, p orbital 3 that can hold 2 apiece, that's 6, and the d orbital we have 5 that can be 2 apiece. Now remember, I already told you in OCHEM, if we're talking about carbon, we're not going to get to the d orbitals. But I'm going to go ahead and give you an example on the next slide of chlorine so you can remember and recall what you learned in Gen Chem about this. So in order for us to fill in these ground state electron configurations, the first rule we need to know is the lowest energy fills first. That's the Aufbau principle. So you start at the bottom. The next thing that happens is we need to know that only 2 electrons can occupy an orbital, one of those lines, and they must be of opposite spin. So the way we note that usually in these structures is we have an arrow going up and an arrow going down, and that shows the opposite spin there. And then the next thing is orbitals of equal energy. So that would be the p and the d orbitals, for example. They can only fill in one at a time, and they're going to pair up last. It's because it takes more energy to pair up last, and that's Hund's rule. So the ground state electron configuration, let's do chlorine. Chlorine has 17 electrons, so that'll give us a few more to play with. After this, we'll go ahead and do carbon, but carbon only has 6. So this is a nice way to remember how we did this. So let's take a look at this. I have to show 17 electrons. How did I get 17 electrons? Is if you look at the periodic table, you'll see that chlorine is element number, atomic number 17. And when you have a neutral atom, the number of protons, which is the atomic number, is equal to the electrons. That's how I got 17. All right, let's go ahead and start this. 1 electron, I have 17, I need 16 to show. Since there's only 1 orbital there, then the next one has to be opposite spin. Now I have to go to level 2. The lower energy would be 2s, so 1 would go into the 2s, and then the second one, it'll go ahead and pair up because there's no other equivalent level, so it would be opposite spin. I've shown 4. So I have 13 to go. Now here's what happens when we talk about only 1 can fill at a time. So on the 2p, what's going to happen is I have, remember the x, y, and z? So we're going to have 1 in each of those. Then if we have more electrons to show, which we do in this case because we have 17 total, then they can pair up. So far I am showing 2, 4, 6, 8, 10. I still have 7 more electrons to go. So let's go up here. The 3s will be next. And then the 3p, remember they don't pair up at first. So let's see how many I'm showing. 2, 4, 6, 8, 2, 4, 6, 8, 10, 12, 13, 14, 15. I have 2 more to show. And there you have it. That's it. That's the ground state electron configuration for a chlorine atom. One of the things I can get from this is we can look at how many valence electrons it has, because remember, it's the valence electrons that are involved in bonding. And if it wants to have an octet, take a look at this. Take a look at this. Pretty cool. The p orbital is the highest. The 3 orbital is the highest, whether it's p or s. And I have a total of 2, 4, 6, 7 electrons. And we know that chlorine has 7 valence electrons. The reason why chlorine can only single bond, or any of the halogens, is because what happens is it has room only for 1 more electron to come in here, and that's it. So it can only make a single bond. All right, let's go ahead and take a look at carbon on the next slide. Go ahead and pause the video. I'd like you to go ahead and fill in the 6 valence electrons in this ground state electron configuration. Come back and check how you did. So go ahead and pause it, fill it in, and then come on back. All right. 1, 2, 3, 4, 5, 6. That's it. We're done. So we actually have an incomplete shell. It's even worse than we have with the chlorine. In fact, if you take a closer look at this, I have room for 1, 2, 3, 4 more electrons. How many bonds does carbon prefer? 4. It's not a coincidence. It's kind of how we know that carbon wants to have 4 bonds. Here's another thing. Now, when we're talking about this 2p and this 2s, this is not a complete octet. And it's going to want to do something. When it meets up with other atoms, it's going to want to do some adjusting so it can bond with it nicely. Remember, it's only the valence electrons involved in bonding, and it only has 4 valence electrons. So let's take a look and see how we're going to handle that. So how we are going to handle the fact that we have those open orbitals is, what happens is, it's under valence bond theory. Bonds are formed by the overlap of the orbitals of atoms. The more overlap, the stronger the bond. So what happens here is, remember I had 3p electrons. Let's move back. I want to go back one time. I want you to see that. It might take me a second to get there. To remember, right here we have a total of 1, 2, 3, 4 electrons, 2 of them in the p and 2 of them in the s. Well, what happens is those electrons in the second level, they actually get together and remember 1, 2, 3, 4 electrons, it makes what's called an sp3 hybridized carbon. And what happens is this is a combination of the S's and the P's. That's why it's hybridized. They're blending. And what's going to happen is one sp3 carbon from one atom can actually bond with the sp3 of another one. And these two electrons, the ones they're showing in these pink balloon things, they're going to share that electron in a covalent bond right here. And that means this bond between this carbon and this carbon, because this carbon is sp3 hybridized. Do you see how these are lowercase letters and this 3 is superscripted? You have to make sure you write them correctly. The S and the P are lowercase and the 3 is superscripted. This line right here is showing a bond line, and it's telling me I have an sp3 carbon bonded to another sp3 carbon. And anytime I have an sp3 to an sp3, it's known as a sigma bond. So let's take a look at that. Sigma bond is the head-on overlap of sp3 orbitals. It's a single bond or the first bond involved, even if you have a multiple bond. Now, what this is not showing, this model right here, is it's not showing you these carbons bonded to anything. So these carbons, remember carbon makes 4 bonds, we're only showing 1. There could be hydrogens, for example, here, halogens, or other carbons. We're only focusing on this first sigma bond that happens between 2 carbons. Another piece of information that you are required to know for this class is when you have a sigma bond, so we are talking about sigma bonds right now, is the bond lengths and the bond angles that are happening. So the bond length between a carbon and a hydrogen, that would be between here and here, is 110 picometers. Where we have a carbon-carbon bond, that bond length is 154 picometers. Yes, you must memorize these numbers. And I'm going to forewarn you that sigma bonds, single bonds, have different bond lengths than when we get to double bonds. Those will be more numbers to memorize, and triple bonds. So know that this is specifically only for sigma bonds or single bond. And then the bond angle on our tetrahedral is 109.5, and we're going to get into more specifics on those later. Okay, we showed you in the previous slide sigma bonds, which is the first bond that's formed. In fact, now we're going to show you another type of hybridization that can happen with our s and p orbitals. This is an sp2 orbital. In fact, this carbon here, this is the shape that's going on here. We have one s and 2 p orbitals that are hybridizing. And do you see these guys right here in blue? They are not involved. This p orbital is not involved in the hybridization. In fact, it's just a plain old p orbital that's going to be happening. But these 3 are involved, 1s and 2p. Do you see how those add up to 3 if this was, 2p's? Do you guys see that? So what's going to happen is we're going to get a different shape molecule. In fact, what's going to happen is this electron and this electron are going to join together our 2 carbons, and that's going to form that sigma bond we just saw. But what's going to additionally happen is these 2 pi bonds that were not involved in the hybridization, those p orbitals are now going to make a second bond, and this is how you see a double bond formed. Now, the first time I saw this, I'm looking at this going, this looks like a triple bond because you have a top part, a middle part, and a bottom part. Well, this is not a triple bond. This is only a double bond. In fact, I have triple bond shown just beneath it. This is the probability where the electron can be, and it's almost a square shape here of where those 2 electrons can be at any one moment. It's this entire region of blue. So this is actually just one bond of your 2 bonds. The sigma is the first bond on your double bond, and this is the second one. And this, in this case, they have this drawn going up and down inside of our slide here. Now, look down here on a triple bond. A triple bond is an sp orbital. Do you notice we're using less orbitals? We only have one s and one p. So what's going to happen is what we have in blue, again, is a p orbital that's not being used. And what they have this time in pink is a p orbital not being hybridized. Now this green one here is going to be an s and p that are together, that are hybridized, and it's going to join to another sp orbital. And you can see here, that's where we're going to get another bond. We actually have 3 bonds happening here. Take a look at this. Each of the unhybridized p blue orbitals will come together. Can you kind of see that here? These pink ones will come together, and it's going to be 90 degrees away from that one here. And then we're also going to have our sigma bond, and this is where our triple bond is going to happen. We have our sigma bond. Remember, the first bond that always happens whenever we get 2 atoms together is our sigma bond. The next one will be a pi bond if it's a double bond. And in a triple bond, we would have a sigma and 2 pi bonds. I have a YouTube video that helps explain valence bond theory and how to draw it. Be sure to take a look at that video that I have posted. All right, let's take a look at pi and sigma bonds, and let's practice labeling them. So we don't want to draw those balloon shapes all the time, and we don't want to show the molecular orbitals all the time, but we can, on a line structure or any kind of organic structure, determine how many bonds are happening and if they're sigma or pi. So how do we do this? Is if it's a single bond, it's a sigma. If it's a multiple bond, it always starts off with a sigma, and then we start adding pi bonds to it if it's a if it's a double or a triple. So let's take a look at this. On our first one up here, nitrogen, it has 3 bonds like it's supposed to. It's single bonded to hydrogen, so that would be a sigma bond, and oops, I made that one wrong, sorry. Sigma bonds. So I have 3 sigma bonds, no pi bonds happening. In fact, if you want to add the lone pairs, you can. But did you notice the lone pairs didn't change how to classify them as sigma or pi? All right, anytime you have a single bond, that's a sigma bond. So this is a sigma, and this is a sigma. Now I have a double bond going on here, so one of the bonds is sigma, but I have a second bond that would be a pi bond, and that's how I would label that. I'm going to come down here. Let's try this example. I have a carbon with a hydrogen. What would that be? If you guess sigma, you're definitely correct. And carbon and hydrogen single bond, that would be a sigma. And in this case, between carbon and carbon, I have 3 bonds. Now remember, you always, anytime 2 atoms come together, the first one is always a sigma. But I have 2 other bonds. That means I would have 2 pi bonds in here. So I would have a total between my carbon and carbon here, I'd have 1 sigma and 2 pi's. And that's how you would note that. So I have 2 other structures on here that I haven't done. I want you to go ahead and pause the video, fill those in, and come back and check your work. You haven't done these, so I'm going to go ahead and show you these. So we have a sigma, a sigma, a sigma, and a sigma. I have 2 bonds. There's always a sigma first. There's only 2 bonds total, so there'd be 1 pi bond. And this time I didn't write the line between there. Do you guys see that? You might not always see these bonds explicitly. So what's between my carbon and my hydrogen? That's a sigma bond. So I went ahead and put an arrow there to show that. And I have a triple bond, so that would be 1 sigma and 2 pi. How'd you do? All right, so explaining the hybridization in a little more detail here. Hybridization sp3 orbitals and the structure of methane. Carbon has 4 valence electrons. In fact, if you did the electron configuration and you only looked at the valence, you'd have a 2s2, 2p2. That's from the electron configuration. These are only, the valence are only the ones involved in bonding. That's why I didn't put the full electron configuration here. So in methane, CH4, all carbon-hydrogen bonds are identical. They're tetrahedral. So we look at this as being an sp3 hybrid orbital. The s orbital and 3 p orbitals combine to form 4 equivalent unsymmetrical tetrahedral orbitals. Okay, take a look at this. Do you see spp? Because it's spp. These guys come together, and instead of writing p 3 times, they like to superscript it right here. That's why it's lowercase, lowercase, and then superscripted. And Pauling came up with this idea back in 1931. And it works pretty well. So we have our 4 different orbitals, and they're hybridized to this tetrahedral shape. Now, on this tetrahedral shape, what we don't normally see is this little node on the other side. They're actually combined together. So typically you just see the tetrahedral shape, but just realize there's a node and then this other little piece over here. If you're asked to draw just a single sp3 orbital, this is what it would look like. If you're asked to draw the tetrahedral, the 4 of them together, it would look like this. sp2 hybridization. Ethylene is an example of that with 2 carbons and a double bond there. sp2 hybrid orbitals. A 2s orbital combines 2 p orbitals, giving 3 orbitals total. So we have spp. Now remember, this one they have in blue here is not involved in the hybridization at all. And in fact, it's going to be 90 degrees away from where this guy is here. And it's only these sp2s that are going to join with another atom's sp2 and make the carbon-carbon double bond, one of them with the sp feature and the other with the p. So the sigma stuff's going to happen with the sp. Notice the sigma's there, and the other one's going to happen with the pi bond, the p orbital, pi, and then sigma. And then this is just a picture of the same thing, just looking down at it so you can see the bond angles and stuff going on. So you have a side view and you have a top view. So the remaining p orbital is perpendicular to the plane of this. How the bond is formed between the two sp2 orbitals is the sp2 hybridized electron here is going to join this electron. We just saw this picture earlier. It's the same picture. And we have our sigma bond. That's the first one that forms. And those two p orbitals, one on each atom, that are not hybridized, they are perpendicular. They're going to form their own bond, and this is the pi bond. P orbitals form pi bonds. These hybridized sp form sigma bonds. All right, let's take a look at the text here. Two sp2 hybridized orbitals overlap to form a sigma bond. P orbitals overlap side to side to form a pi bond. We now have an sp2. Take a look at this, guys. sp2 bonded. This isn't a minus sign. This is showing a bond line. We have an sp2 sigma bond and a 2p pi bond result in the sharing of 4 electrons, and we get a carbon-carbon double bond. Electrons in the sigma are centered between the nuclei. Electrons in the pi bond occupy regions on either side of a line between the nuclei, and you can see that right here. All right, so taking a look at these, the double bond, the sp2 numbers that you do need to know, we have a carbon-hydrogen length of 107.6 picometers, whereas we have a carbon-carbon double bond. It's actually shorter than the single bond, 133 picometers, and yes, you do need to know these numbers for all of these. The bond angle, now normally when we talk about a carbon-carbon double bond, we generically say it's 120 degrees. That's just kind of a brief way to do that, kind of an average. But now that we're at the higher level, you do need to know the actual bond angles, and they are different. You need to know that the hydrogen carbon-carbon bond angle is 121.7 degrees, where the hydrogen carbon-hydrogen is 116.6. So when you're asked for these specific angles, you must give them. You cannot give an answer of 120. You do have to know these numbers specifically. The triple bond is sharing 6 electrons. 2s orbital hybridizes with a single p orbital, giving us 2 sp orbitals. The 2 other p orbitals remain unchanged, and they're showing you those in the blue here. So here's the first p orbital going up and down the axis. This one's going this way. Now this one here in green, it's not just a p orbital, it's a hybridization of 1 s and 1 p. So 2 p orbitals remain unchanged. sp orbitals are linear, 180 degrees apart on the x-axis. The 2 p orbitals are perpendicular on the y-axis and the z-axis. So this is the common name is acetylene, and this is when we have 2 sp orbitals. So this is that similar picture that we already saw. In fact, I think this is the exact same one I had before. Now we can see how they're coming together here. And so we have 2 sp hybrid orbitals from each carbon form an sp bond to another sp sigma bond. This first bond right here is an sp to sp sigma bond. And then this right here would be similar, the one in blue is similar to the pi bond we saw in the double bond going up and down, whereas the new feature is we've got the orbital going 90 degrees away from that. That is our triple bond. That is the third bond going on. pz orbitals from each carbon form a pz to pz pi bond by sideways overlap, and py orbitals overlap similarly. And here we go with knowing some more numbers. So on a triple bond, our bond angle is 180, regardless if we're doing hydrogen, carbon, carbon, or carbon, carbon, hydrogen. The bond length between carbon and hydrogen in a triple bond, or in this case an sp hybridization, is 106 picometers. And we have a shorter bond than we've had before between carbon and carbon. On our triple bond, it's 120 picometers. So again, you might want to make a table of this where you have your sp3, sp2, and sp, and maybe write down the different bond angles and the different distances on the bond distances so you can compare them and make sure you learn all of them separately. You need to know all of them. So here is a molecular orbital drawing link. One of the things you're required to do for this class is to be able to draw those orbitals. And so I made a video, and right here, the format I'm using right now isn't supporting the video itself, so you can't see it. It's highly likely if you go back to the PowerPoints I have that are not on video, the ones that are just posted where you can go through the slideshow, most likely you can just get to that. So be sure to look at that. Or I also have the link here, so you can just go ahead and click on the link. So I'm going to go ahead and click on the link. And what's going to happen is you will be directed. All right, I'm going to go ahead and pause that. So if you go to that link, what's going to happen is I'm going to show you how to draw the molecular orbital picture, and you can see on the background there for an alkane single bonds, alkene double bonds, and alkynes triple bonds. So be sure to take some time to look at this video. Hybridization. So one of the things organic chemists like to do sometimes, instead of telling you bond angle, bond lengths, and the geometry like linear, trigonoplanar, sometimes we like to just say, hey, the carbon is sp2 or the carbon is sp3, and then we know all the other pieces about it. So if it's sp3, I know it's 109.5 degree bond angle, I know it's tetrahedral, and I know all the bond lengths. So that's a shortcut way of us describing carbons. So generically, I have here sp is 180 degrees and the shape is linear. And the reason why I'm saying generically, because on an sp2, we know that there's actually more specifics, that 116 and that other number there. So 121. So make sure if you're using 120, it's more a generalized. I most likely will be asking you for the specific number on the exam. So make sure you know the specific number. And that's known as trigonoplanar. And sp3 is 109.5 and tetrahedral. You need to be able to look at a compound and be able to tell me its hybridization, its bond angle, bond length, and geometry on all atoms in the molecule. So instead of you drawing out all those structures and all the molecular orbitals, sometimes you're just going to be given a structure or maybe a condensed structural formula, and you need to be able to tell me the hybridization around all of them. So first of all, if something is only bonded one bond, like halogens and hydrogen, there is no hybridization at all. So you're not going to be looking at that. You're only going to be looking at atoms that have two or more bonds. So I have a nice way, a shortcut to do this. So you're going to have a new way to count. And this will make more sense as we use it. So bear with me for a minute, but this is the new way to count. You know, how we would count, for example, sometimes would be 1, 2, 3, 4, or we would order things. We'd say A, B, C, D, you know, those kind of things. So, all right, so let me show you how this works. Another thing we need to keep in mind is multiple bonds and lone pairs count as one if we're going to use this technique here. All right, so we can't do anything about the hybridization around hydrogen because it's only bonded to one. There is no hybridization. This carbon, let's do this carbon here first. I think this one's easier to see because it's explicitly shown. Now, the new way to count is you're going to count sp2. Remember, multiple bonds count as one. sp2. This is an sp2 hybridized carbon. sp2. Do you see how I just went around the circle here and started counting them? And that's the easiest way to do it. Multiple bonds count as one. Now this carbon over here is written with 3 hydrogens. What's really going on there is, I'll expand this out for you, is you actually have 3 hydrogens coming off that one carbon. So if I were to explicitly show you those 3 hydrogen, it's bonded to the carbon here, and we won't worry about the rest of the molecule right now. So this is this carbon here, this is this carbon here. Take a look at this. If we were to count sp23 in that order, let's count all the bonds around here. Ready? sp23. Did you notice? Listen to what I said. sp23. It sounds like I ended on sp3. sp23. sp3. This carbon is sp3 hybridized. Let's look at this one again. sp2. See how it ended there? It's a nice little shortcut. Let's take a look at this carbon right here. Let's count around and count it out loud with me. Ready? sp2. What's the hybridization around that carbon? sp2. Let's take a look at this carbon right here. Now remember, multiple bonds count as one. sp. That's it, it's sp. And notice it is a triple bond and a single bond. This carbon is sp hybridized. Well, what about this guy here? sp. In fact, I'm going to cheat a little bit, use the same sp and just bring an arrow to it. Both of these carbons are sp hybridized. Now again, we don't do hydrogen because it's not bonded to more than one thing, but oxygen is. Now here's a case where I'd want to go ahead and fill in my lone pairs because multiple bonds count as one, and we handled that here under sp, but lone pairs also count as one. And this has two lone pairs. We have to count both of them. So when I want to know the hybridization around oxygen, because yes, other atoms other than carbon can have hybridization. Let's take a look at this. We're going to count each lone pair as we go around. sp23. This is sp3 hybridized. Oxygen is sp3 hybridized. It has that bent angle because it has two lone pairs. Okay, we can do the same thing. This is explicitly shown, but what if we happen to have a molecule that shows this line structure here? We can do it on this too. So let's take a look at this carbon right here. This carbon right here. What's really going on here is it has, anytime we have a ring structure, anytime I have a bend or an end, I have a carbon there. And so in this case, in this ring structure, I have 1, 2, 3, 4, 5 carbons. So this would be 5 carbons in a ring. This carbon is single bonded to this carbon over here. And this guy's got more bonds going on. We'll look at those there. So if I wanted to know the hybridization around this carbon, one of the things that's not shown in this kind of structure is the fact that each carbon must have 4 bonds total. So this carbon right here actually has 2 hydrogen atoms on it that I'm not showing. And this is the kind of drawings you're going to get a lot more often in OCHEM, especially this upper division. So when I want to know the hybridization on this carbon here, I can't forget that there's also 2 hydrogens there. So when I go around and count, I need to remember these guys. So it'd be sp23. So this carbon right here would be sp3 hybridized. And that makes sense because there's only a single bond showing. Well, what about this carbon here? Do you notice it's the same as this one? It doesn't have hydrogen shown, so it'd be, if you take a look at it, it would have the 2 hydrogens, so it'd be sp23. This guy right here is also sp3 hybridized. Remember, I don't want to fill in the hydrogens all the time, but you can see this is identical to this. It has 2 hydrogens, sp23. And in fact, if we take a closer look, this carbon is sp3, this one is sp3, and this one is, it has 3 single bonds shown to carbon, but what's not being shown is a bond to hydrogen. So that is also sp3 hybridized. Anytime we have single bonds happening, guys, it's sp3. All right, let's take a look at these multiple bonds. This carbon right here has a multiple bond. What is the rule on multiple bonds? Multiple bonds count as one. So this carbon right here, let's take a look at this one here. Let me give myself an arrow so you know which one I'm talking about. This would be, would this have any hydrogens on it? Let's check. It has 1 bond to carbon this way. It has a single bond to carbon there, that's 2. It has a double bond to carbon here and here, so that's 4 bonds total. Does this need a hydrogen to make 4 bonds total for carbon? No, in fact, this has no hydrogens on it. So this would be it. It has its 4 bonds total. That's why we had to start off knowing carbon has 4 bonds. All right, so let's take a look at this. We have sp2. This is sp2 hybridized. And we did learn that when we have a double bond, it's sp2 hybridized. What about this carbon here? Let's see. Does it have a hydrogen? I have a single bond to carbon here, so that's 1 bond. It needs 4 total. It has another bond to carbon here and another bond to carbon, and that's 3 bonds to carbon. So yes, this one does have a hydrogen that's not shown in the line structure. So when I count and try to figure out its hybridization, it's sp2. So this one is also sp2 hybridized. So what do you think this one, this one, this one, and this one is? Go ahead and pause the video, fill it in, and come back and check. All right, in fact, these are all also sp2 hybridized. So we talked about the atom, what's in the atom, where the electrons are located, how the electrons hybridize, and how they bond together. So now let's take a look at what's known as molecular orbital theory. Now we're going to make molecules. We're going to put two different atoms together, and again, that's called molecular orbital theory. This is where electrons are most likely to be found. The specific energy and general shape of a molecule. What happens is we have additive combination, which is bonding molecular orbital. It's lower in energy than the original energy that the came in the first place. So here I have hydrogen, a 1s orbital at this energy. What happens is over here I have another hydrogen 1s at this energy, and when these two come together, when they bond, if this is a lower energy than what started, then that means it's a bonding orbital. If, and you've seen these drawn before, if the bond is higher in energy than the original, then it would be anti-bonding or unfilled, and that's not what's going to happen. So anytime we look at a molecular orbital diagram like this, anything that's below the original level is possible for bonding. Anything above it is going to be unfilled and anti-bonding. When we have ethylene, ethylene is the common name for two carbons together, double bonded to each other. So here is the formula for ethylene. Carbon double bonded to carbon, each has two hydrogens. The pi bonding molecular orbital, notice we have two orbitals coming together at this energy level. Notice this is higher energy than this. Higher is not going to happen. That's going to be our anti-bonding molecular orbital. Not going to happen. This is lower energy. This is down here. This is what's possible. So typically when we have two p orbitals, what they'll do is they'll go ahead and, do you see how these top lobes are the same color as each other, and these two bottom lobes are the same color? Sometimes in textbooks or on exams, they'll show it by having shaded and unshaded as opposed to having colors. So only time that these two will come together, what they did was they flipped it here. You can't have opposite together. It's always the same color. So this is where we have this node and this come together. Remember, all of this, both in pink and blue, will bond. The probability of where the electron would be at any one moment, they move really, really fast, would be this entire region, this whole region that looks like a square. So that's it for part one, information on your lecture notes. How I've done this is I try to break up these lecture videos into different parts so they're not as long and you have a chance to kind of digest the information. So this is it for exam one material part one, and I'll be back with you for exam one material part two in another video.